Hello, welcome to my channel. A long time no see. So I was very busy during the times I couldn't upload any videos. So, uh, but now I am back with a new video on the circuit response, the time and frequency domain analysis. So, in this part, I'm gonna discuss about the step response of the series RLC circuit. So in my previous video on the circuit response in electrical system response, I derived the equations for the source free response of the series RLC circuit and parallel RLC circuit in both time domain and frequency domain. Now I'm gonna derive the circuit response equation for the series RLC circuit uh, when the input is a step function or a DC value. Here the DC input is the excitation is DC, which is Vs. So I'm gonna derive the equation in time domain and frequency domain. So as you can see, I have already done some basic elementary derivations in shortcut, because I have already done the transient response derivation in details in my previous videos. So uh, you go and watch those videos if you don't understand this shortcut derivation. So I'm gonna straight go to it. So this is the series RC circuit, and electrical systems are mainly linear elements. When there's only R, resistor, inductor, and capacitor, because these elements are linear, and these are passive elements. They are not active elements. So the principle of superposition, the superposition principle, can be easily applied, and we can easily um, uh, use the Kirchhoff's current and voltage law. So by KVL, current through all the elements in the loop is R plus LDD is the differential operator, linear differential operator, which is d by dt, and 1 by d is integration. So R plus LD plus 1 by CD, uh, bracket, then the whole thing is crossed, multiplied by the loop current, which is equals to the input, which is the DC value Vs. Now I have just rearranged it, and this is the differential equation. So this is the linear differential equation with constant coefficient. Here the constant coefficients are the coefficient of d square is 1, the coefficient of d is r by l, and 1 by lc is the constant. Now, so this is the linear differential equation with constant coefficient. So we have to um, solve this differential equation and get the appropriate uh, answer, the solution, the appropriate solution for the circuit. So I have assumed the circuit response is the loop current, and the now we know that the a linear differential equation has two parts as its solution. One is transient part and the other is particular integral part. The transient response, or also it can be called the complementary solution. So complementary solution can be found by uh, taking the characteristic equation. So the complementary solution can be easily found by solving the characteristic equation of the differential equation. So the characteristic equation is this part. So d square plus r by l d plus 1 by lc equals 0. Now what we have to do is we just have to find the roots. The roots are also called eigenvalues. So here I have found the roots. Roots can be denoted by lambda 1, lambda 2. which is sigma s minus sigma s plus minus j omega d. Here sigma s is the damping factor for the series RLC circuit, which is R by 2L. For parallel RLC circuit, the damping factor is 1 by 2RC. So there's some differences in the different orientations of systems. The damping factor varies depending on the orientation of the electrical systems, depending on the orientation of the elements, the passive elements, mainly resistor and mainly resistor. Omega d is the damped natural frequency, which is omega n root over 1 minus zeta square or chi square. Omega n is undamped natural frequency, which is 1 by root LC. And so zeta is the damping ratio is r by 2 root over c by l. So here I can also here I can also tell you how I found it. So this is just, as I said, this is the ratio of the damping factor and the undamped natural frequency. This gives the ratio of these two gives the damping ratio, this value. So these are the two roots, minus sigma s plus minus j omega d. So which is lambda 1 lambda 2 the eigenvalues, and for which for these two roots the transient response of the circuit is c1 e to the power lambda 1 t plus e to the power lambda 2 t. And we can decompose this, and we can find the Euler's formula. We can find another expression for the transient response, which is c3 cos omega dt plus c4 sin omega dt, and the whole thing is multiplied by e to the power minus sigma st. So this is the whole transient response of the series RC circuit with input or without input. Now we're gonna find so so now that we have found the transient response, all we have to do is find the arbitrary constants, which are c3 and c4. But we are going to find it, but before that, let me find the particular integral is the steady state response of the circuit of the electrical system. So particular integral is basically 1 by L d by d square plus r by L d 1 by L c vs is the dc value. Okay, so d is the differentiation. If we differentiate vs, which is a constant value, it will give us 0 altogether. So current in the series RLC circuit, uh, the current response, the steady state current response of the series RLC circuit is 0. And it is obvious because in steady state there will be no current, and the capacitor, the voltage across the capacitor will be vs, the input value, the dc value. So there will be no current because the um, at this node and at this node, from this node to this node, the voltage difference will be 0, so no current will flow. So this is obviously right, there's no doubt about it. Now we have to find the arbitrary constant. And if you have already seen my previous video on this, on the source free RLC circuit response, that I have already derived the arbitrary constants, but because there's a source in this um, configuration, so I have to find the arbitrary constants again, but I will do it uh, a bit in a bit shortcut way. To find the arbitrary constant, uh, we have to assume that there's initial voltage and current in the storage elements, the energy storage elements, the dynamic elements. In the circuit, the dynamic elements are the inductor and capacitor. So inductor stores energy in magnetic field, thus it has initial current. It may have initial current, and in this case, I'm gonna assume the initial current through the inductor is zero, and initial voltage across the capacitor is also zero. So there's an initial current voltage. But in my previous video, in deriving the response of the source free series and parallel RLC circuit, I assumed that there was indeed initial current and voltage, but in this case I'm not. So the only thing I have for myself is the transient introduced by the input voltage, which is the DC value. So what I'm gonna do is, so at initially the current through the inductor is zero because there's no assumed initial current. So it equals zero. So it equal zero, which is C3 cos 0 plus C4, so C3 cos 0, C4 sin 0 e to the power 0. So also what we have is IO, and this is C3 plus everything is 0, and I have assumed IO is 0, the initial current through the inductor, so C3 is also 0. So our first arbitrary constant is 0 here, so there's no problem in that. Now what I'm gonna do is I'm gonna find the arbitrary constant C4. So for that I'm gonna find the voltage across the capacitor. So voltage Vct, which is function of time across the capacitor, is integration 1 by C it, the loop current dt, plus a constant. So this is the, sorry, a constant, say the constant is, if we um, observe the circuit, we will easily see that the initial by initial condition, this constant is basically plus minus Vs. There's no doubt about it. If you uh, try if you observe this carefully, or you can derive it. I'm not deriving it, this is just basically evident. If you practice regularly, you will find it mainly very easy to understand which is what. Mm, at this point we can safely say that the arbitrary constant C3, which is always multiplied to cos omega dt, this C3 is always without no doubt is IO, which is the initial current through the inductor. So here this constant is basically, so let me write it. So at time t equals 0, this at time t equals 0, Vc is voltage across the capacitor is the initial voltage, and 1 by C this say this is minus vs. Okay, so I have as so if I take this minus vs and to the left side, it will become vo plus vs equals to 1 by c it dt, and I have assumed vo 0, so vs equals to 1 by c it dt. I'm not deriving this integration. I will just write it as it. So it will basically give me the c4. Okay, at t equals 0, at t equals 0. So this is basically it. So this is c4 is the vs. So for the step response, okay, there was no input, the c4 would be only the initial voltage, and I have assumed the initial voltage across the capacitor is 0. So c4, the second arbitrary constant, which is multiplied by sine omega dt, is vs. Now the transient response of the series RLC circuit becomes c3 is 0, so 0 cos omega dt plus v vs by omega dl. I have forgotten to tell you that c4 is mainly c4 is vs by omega dl, because when I wrote this 1 by c it dt, it will give you omega dl at t equals 0, omega dl c4. This is the basic uh, derivation. I had forgotten to tell you. So vs by omega dl, so c4 is vs by omega dl. So vs by omega dl sine omega dt e to the power minus sigma st. So because this is 0, so it will be vs by omega dl sine omega dt e to the power minus sigma st. So now the complete response does. So the answer is vs plus omega dl sine omega dt e to the power minus sigma st. So this is the complete response for the series complete response for the series RLC circuit when the input or excitation is a DC or a step function. So this is the answer. So I have derived this in time domain. Now I'm going to derive the same this equation and prove it that it is the same, the response is the same in the frequency domain. What I'm gonna do is I'm gonna apply KVL again, and it will give me R plus SL plus 1 by SC IS, which is VS by S. L, if we take common L by S, it will give us S square plus R by LS plus 1 by LC IS, which is VS by S. Now S square plus R by L S plus 1 by LC IS, which is VS by. So if you see, if I take this L by S to the right hand side, it will the S will cut out and it will leave VS by L. VS is the DC value. Now what I'm gonna do is is 1 by L Vs by S square plus R by L S plus 1 by LC. So I'm gonna factorize this. So I have already done this same derivation in my previous video, so go watch it. I'm gonna in this video I'm gonna just make uh, apply all the equations and go for a shortcut. Okay, so here 1 by L, if I take the Vs out, this is just DC value, it doesn't have S in it, so it is not a function of frequency. So I will take Vs by L out. So now one I'm gonna just factorize this, the denominator. So S minus lambda 1, S minus lambda 2. If I take it like this, so here Vs by L A by S minus lambda 1 plus B by S minus lambda 2. So I have to find the A and B, which is unknown. So finding the arbitrary constant. So let us find it. So A S minus lambda 2 plus B S minus lambda 1 is equals to 1, which is this. Um, I have just, I hope you understand what I have done. So here is A into, sorry, A plus B into S minus A lambda 2 plus B lambda 1. Now if we equate the coefficients on both sides, on both left hand side and right hand side, it will give us A plus B equals 0. If we take A equals to minus B, then A lambda 2 plus A lambda 2 plus B lambda 1 equals to minus 1. If I take A equals minus B, then it will be B equals to lambda 1 minus lambda 2 equals to minus 1. Thus B equals to minus 1 by lambda 1 minus lambda 2, and A equals to plus 1 by lambda 1 minus lambda 2. So we have found our lambda 1 A and B, which is Vs by L. Lambda 1 lambda 2 are eigenvalues, so these are 1 by S minus lambda 1, lambda 1 minus lambda 2 minus 1 by S minus lambda 2, lambda 1 minus lambda 2. If we take the lambda 1 minus lambda 2 out of the bracket, it will look like this: lambda 1 minus lambda 2, 1 by S minus lambda 1 minus 1 by S minus lambda 2. Now what I'm gonna do is, we know, if go watch my previous videos, lambda 1 minus lambda 2 is 2j omega d. It is just, so basically what lambda 1 and lambda 2 is, lambda 1 is minus sigma s plus j omega d, and lambda 2 is minus sigma s minus j omega d. So if I subtract these two, it will give us 2j omega d. So vs by 2j omega dl, and 1 by s minus lambda 1 minus 1 by s minus lambda 2. So if I take the inverse Laplace of the current response, it will basically be 2j omega d e to the power lambda 1t minus e to the power lambda 2t. Now if I apply the Euler's formula, it will give me easily Vs by omega dl, and 2j, if I take it here, it will give me sine omega dt e to the power minus sigma st. This is so easy. So this is the same as the derivation I had found in the time domain analysis. Okay, so this proves the validation of the uh, response, circuit response. I have derived the current response in both time and frequency domain. So just let me summarize this. So this is the part. This is a transient part. This is just like, this is t and this is it. So it is like this. And because current goes to zero at steady state, the voltage across the capacitor is Vs. So this aligns with the idea that at steady state there is no current in the RLC circuit. If you apply DC in a RLC circuit, series RLC circuit, there's no current. If we consider on a DC part, so there's no current. Obviously this is just a transient part which decays over time. So this is the full response of the series RLC circuit, and I will not be making a video for parallel RLC circuit for step response. If you see my previous videos, you will obviously understand the derivations are quite same. So for the parallel RLC circuit, if I take a current source, so say current is going here, this is current source and this is the parallel circuit in both time domain and frequency domain. If I take the voltage as the circuit response, voltage is this Vt, this is the direction of the current I have assumed. So IR, IL, IC. So the voltage response will basically be the same. It will be, if I assume initial current and voltage is 0 through and across the inductor and capacitor respectively, it will eventually give me this is by omega dc. It should be sine or cos, I have forgot, sin omega d e to the power minus sigma pt. So here sigma p is the damping factor of the parallel RLC circuit, which is 1 by 2 RC, and omega d is the same as always, omega n 1 minus the damping ratio is squared, and omega n is 1 by root LC, and that's basically it. So this is the circuit response to the uh, DC input for the parallel RC circuit, which is the voltage response, the node voltage, which is Is by omega dc sine omega dt e to the power sigma pt, and the current response is Vs by omega dl sine omega dt e to the power minus sigma st. So check it yourself. If you find any mistakes, you can tell me. I have assumed initial voltage and current, assuming vo equals 0, io equals 0. Thus this is the whole circuit response for the series RLC circuit, and I have been done the derivation for the parallel, but you can uh, I can confidently say that the current response, sorry, the voltage response for the parallel RLC circuit, the circuit response for the parallel RLC circuit is basically this. There's no doubt about it. Okay, so overall, the circuit response for the RLC circuit is for the series RLC circuit this Vs by omega dl. Vs is the value, DC value of the input, and omega dl, omega d is damped natural frequency, sine omega dt e to the power minus sigma st. Sigma s is this the damping factor for the series RLC circuit. So that's it. Thank you for watching this far. I hope you understood my explanations. If you have any doubts and anything to add, you can tell me, and I will try to um, re revise my uh, video and try to address those in my in the later videos. So thank you for watching.